All right, so we're going to do these last two problems that we didn't get to finish in chapter 3 in class. So this first one, we are drawing the correct Lewis structure. So we have CHCl3. So we're going to do our needed, available, and shared method. Carbon wants, there's 8 valence electrons, and there's only one of them. Then we have hydrogen. Now be careful. Hydrogen is happy with 2. Remember? It'll go over, add one more, it'll look like helium. Helium's one of those cool kids, so it'll be happy. We have one of them, and then we have chlorine, which also wants 8, and we have 3 of them. Okay, so that's how many we need. How many are available? Well, in carbon, I have 4. In hydrogen, I only have 1, and I have 1 of them. And then chlorine, I have 7 valence electrons in each chlorine, and I have 3 of them. So if I add up my needed is 34, my available is 26. And then what I get for my shared, the difference between the two is 8. So these are 8 electrons that are going to have to be shared. We divide by 2 and we get 4 bonds. Okay. So we always do our available minus our shared. Our available, we had 26. We're going to subtract out our shared of 8 and we get 18 electrons left. Okay, so let's see if we can draw our structure that fits that. And so we have to decide what's going to be our central atom. We know that chlorine is a halogen. It's in group 17, so it can only really make 1 bond. Hydrogen can only make 1 bond because it only needs 1 more electron to complete its octet. So it ends up being carbon that is our central atom. So we put 1 carbon in the middle, and we're going to put a hydrogen, a chlorine, a chlorine, a chlorine, and we're going to connect them with bonds. Now we have to go in and assign these 18 electrons that we have left. And so when you go in and do that, what you're going to see is that hydrogen's happy. It doesn't need any. Chlorine's happy. It doesn't need any. So we're actually going to go ahead and stick them right onto the chlorines. So we have 1, 2, 3, 4, 5, 6, and that completes chlorine's octet. 1, 2, 3, 4, 5, 6. That completes chlorine's octet. And then 1, 2, 3, 4, 5, 6 on this chlorine, and that completes chlorine's octet. So 6, 8, 12. So the reason that you're assigning these electrons to these places is so that every single atom has a complete octet. So you look at each individual chlorine, that's 2 electrons here, 2 here, 2 here, and 2 here for 2, 4, 6, 8 electrons. So everybody wants that complete outer valence shell. Okay, let's see. I think I need to add some more room here. All right, so let's do B. In this case, B was AsCl3. So this is actually a poison. This is actually sort of interesting. So do your same thing, needed, available, shared. So how many do you need? Each one of those atoms, we have 4 atoms, each one is going to need 8. So you could do this as acetylene needs 1, needs 8, and there's 1 of it. Chlorine needs 8, and there are 3 of it. Or you could just do 8 times 4. Same thing. Okay. Available. We have 5 available and 7 times 3 available. And so we get a total of 26. So you're always going back to that periodic table and seeing what column those elements are in and how many valence electrons they have. My difference between the two is 6. So I have 6 electrons, divide by 2, I get 3 bonds. Now, do I have any electrons left over? Well, my available minus my shared, I had 26 available, I shared 6, I get 20 electrons left. And you usually assign them in pairs, so you could say 10 pairs of electrons, however you want to do that. All right, so now let's draw it. What's going to be our central atom? Well, chlorine can't be it, right? Because chlorine's got a complete octet, so you can't put chlorine in the middle. So we're going to end up putting chlorine around our central atom, Cl, Cl, Cl. So what I notice about my central atom is that it does not have a complete octet. I have 2, 4, 6 electrons around my central atom. It's not happy, right? How do I make it happy? I give it one more pair of electrons. Now these are lone pairs, they're not bonded pairs, but we still have a complete octet. Now I'm going to go around and give them to my outer elements so that they all have complete octets. So I put 3, 6, 7, 8, 9 pairs, and then 1 pair on my central atom, and I used up all 10 pairs. Okay. All right, let's see. So now we're doing C. C, we have Cl2. Now, you could go through needed, available, shared and do it that way, and I'll do it, and then I'll do it a little short way. Needed, available, shared. So chlorine, each of my chlorines wants 8 electrons, and there are 2 of them, so I get 16. Available, each chlorine has 7, and I have 2, so that's 14. So my difference is 2 electrons. Divide by 2, I get 1 bond. And then my available minus my shared, I have 14 available. I'm going to share 2. Wow, I got a lot left over, right? I got 12 electrons left over to assign. So I would put my 2 chlorines. Anytime you have 2 atoms, you just put them side by side. We're going to connect them with 1 bond. And then we have 12 electrons. Well, 12 divided by 2 is 6. So each atom needs 6 electrons, right? Now, the other way that you could do this is that you could say, okay, I know I have 2 chlorines, and then you draw the valence electrons around chlorine. 1, 2, 3, 4, 5, 6, 7. Chlorines 1, 2, 3, 4, 5, 6, 7. And so what I see is that each chlorine has this 1 electron that's hanging out right there. And so what they're going to do is they're going to share those electrons with each other and turn it into a bond. You get the same thing. Same thing. Okay, got to do another page. All right, last one, D, C2H2. So what are we going to do for C2H2? Let's do needed, available, and shared. My carbons need 8, and I have 2 of them. My hydrogens only need 2, and I have 2 of them. Gives me a total of 20 electrons needed. I have 4 electrons in carbon, 2 of them. I have 1 electron in hydrogen. I have 2 of them for a total of 10. So my shared is going to be 10 electrons. I'm going to divide that by 2. So I get 5 bonds in here. I'm going to take my available minus my shared. I had 10 available. I shared 10, none. So I'm going to have no lone pairs on this structure. So what's my central atom going to be? Well, here's the thing. If I put carbon as a central atom and then put 2 hydrogens around it and then put another carbon, there's absolutely no way that I can make this structure work. Because if I give 5 bonds, 1, 2, 3, now I can't make any more bonds with hydrogen because hydrogen's got a complete octet. 4, now my central carbon has a complete octet, but my other carbon doesn't. So this is not working. So what ends up happening is you kind of have to remember that carbon likes to make 4 bonds. So if you take carbon and you give it 4 bonds, well, what could it be bonded to? So we can give it some hydrogens, that's fine, but we also need another carbon to bond to it. So I'm going to put my other carbon first. So I know that I only have 2 more hydrogens to add, and this carbon has 4 bonds around it. I can't put those 4 bonds there. So what I'm going to do is I'm going to take those bonds and put them between the carbons and form a triple bond, and then just give each carbon 1 hydrogen. So it's just kind of moving the bonds around until you see that, okay, my central carbon here has 1, 2, 3, 4 bonds. So that's 8 electrons around it. This carbon here has, let's do a different color, 1, 2, 3, 4 bonds around it. So it's got 8 valence electrons. It's happy. And each hydrogen has 2. So they're happy. So it's just kind of playing around with it and trying it out until you get one that fits. All right, so the last thing we have to do is we're talking about polarity, right? Do we have polar bonds and do we have a polar molecule? So it's twofold. You have to be able to draw the Lewis structure, and then you have to look at the polarity. And polarity is all about the sharing of electrons. How equally do you share electrons? So let's look at our first one. A is CH3Br. And that is a terrible color. Let me change colors so it might be a little bit easier for y'all to see. Okay, so A is CH3Br. Okay, so it's telling me that carbon is the central atom. So I'm going to assume that you can draw the structure. Carbon's the central atom. It's going to have 4 things around it, right? So likes to make 4 bonds. Hydrogens only make 1 bond, and bromine is our halogen, and it only makes 1 bond, and so it's going to have all these valence electrons. Okay, so this is our structure. So the question is, are there polar bonds? To know if you have polar bonds or not, what you do is you go and you look at the electronegativity difference between the atoms. Let me pause this and I'm going to pull that up. Okay, so I pulled it up and I want you to remember, you go to Moodle and you go to exam 2 and you go to resources available for exam 2. And so that's what I've pulled up right here. And this is kind of at the bottom, right? So you get your periodic table, your equations, your polyatomic ions, then here's your electronegativity values. So in order to determine if we have polar bonds, what we need to look at are these electronegativity differences. So we have carbon-hydrogen bonds. And if we look here, carbon-hydrogen, well, they're really, really similar. So they share electrons pretty equally. But if you look over here, carbon and bromine. So here is bromine right here. Carbon and bromine have a large enough electronegativity difference that we say that they do not share equally. So if you kind of remember that fluorine is the most electronegative element on the periodic table, remember fluorine the floozy, she just wants all those electrons. You can kind of remember that. So the bromine is going to have a higher electronegativity, so it's going to want those electrons more. And so you're actually going to end up having a polar bond there. And so what we do to denote that bond is we draw a single arrow and we point at the more electronegative atom. So bromine's more electronegative than carbon, and so we point at it. So that's part 1, right, was draw the Lewis structure, then label the polar covalent bond with a dipole moment arrow. We just did that. And part 3, determine if the molecule is polar or nonpolar and draw the dipole moment arrow for the molecule. Okay, how do you determine if this is a polar or a nonpolar molecule? The question is it symmetric or not? So if you have a molecule, it is polar, P-O-L-A-R, polar if you have polar bonds and the molecule is asymmetric. So if it's not perfectly symmetric on one side or the other. And so if we look at this molecule, what we're going to see here is that one of the 4 has a polar bond, but the other 3 don't. And so it ends up actually pulling all of the electrons and making one side of the molecule negative and the other side of the molecule partially positive. And so we have an overall dipole moment, do kind of a bigger arrow, that goes in this direction, right? And so that's our big overall dipole for the whole molecule, because this area tends to be partially negative, and this area tends to be partially positive. And that's what a polar molecule is. Okay, so let's go back and do B, HF. So hydrogen can only make 1 bond. It only has 1 electron. Fluorine has 7. So it's going to make that 1 bond with hydrogen. So if we look at this, we know fluorine over here. Oh, and I'm not on the screen. So hard. So many different things. Sorry about that. So hydrogen only has 1 electron. Fluorine has 7 valence electrons. So they're each going to share 1, and then the rest go around fluorine. Okay, so if we look at, oh, where did that go? Y'all. It's showing it's still mirroring, and I don't see it. Let's see if I can get it back. So if we're comparing fluorine and hydrogen, That's a huge electronegativity difference. So fluorine's more electronegative than hydrogen. And so fluorine is going to steal those electrons. See, fluorine here is going to steal those electrons from hydrogen. So all the electrons are going to want to hang out over here by fluorine. So if we draw a dipole moment for that single bond, right, we're going to point at the fluorine and put the kind of plus sign by the positive side of the molecule. Now, if I want to draw a dipole moment for the molecule, there's only one bond, right? And we're saying, okay, it's got a polar bond and it's not symmetric. Like if I drew a line here, you'd have to have hydrogen on the other side for it to be symmetric, or fluorine here and a fluorine here to be symmetric. So this whole molecule has a dipole moment like this. So in this case, it was really easy because the bond and the molecule are the same. So then we have PBr3. See if I can change this. Come on. PBr3, okay? So our phosphorus and then 3 bromines, Br, and our bromines are going to end up having lone pairs, right? And then to complete our octet on phosphorus, you're going to have 2 on there, okay? So if we look on our, over here, if we look at phosphorus and we look at fluorine, that's a pretty big electronegativity difference. And fluorine's going to want the electrons more. So we're going to draw our bonds to point towards bromine, right? Oh, I think I compared the wrong one, but here, bromine, here. It's bromine and phosphorus. So bromine still wants it more. So bromine's pulling those electrons. So we got to show that bromine's pulling those electrons. So think about this. If I have 3 of these arrows basically pulling down on phosphorus, what's going to happen to that overall molecule? That these electrons are going to end up wanting to sit down here. So this is going to be my partially negative area, and this is going to be my partially positive area. So if I wanted to draw one overall dipole moment, right, we know that this is not a symmetric molecule, we would draw something that looks like this. So the bottom half of the molecule down here is partially negative, the top half is partially positive. Okay, last one. We have OF2. Fluorine's going to be on either side of oxygen, right? And that oxygen is going to need 2 lone pairs in order to complete its octet. And remember, these lone pairs are taking up lots of space, and so they kind of push down on the bonds with fluorine. So that's why fluorine I have kind of at an angle. So 1, 2, 3, 4, 5, 6 to complete fluorine. Completes fluorine. Okay. So now, are oxygen and fluorine, do they have the same electronegativity? No. Fluorine is going to be more electronegative than oxygen. I just lost my thing again. So the electrons are going to be pulled towards fluorine. See if I can get this back again. I don't know why it keeps dropping me. There we go. So our fluorine is going to keep pulling those electrons from oxygen. And so we're going to have a bond that points at the fluorine, right? Because our electrons are hanging out at the fluorine more than they're hanging out with the oxygen. And so I end up having an area down here that's partially negative, and I end up having an area up here that's partially positive. And so if I want to draw my overall dipole moment, right, I draw like this. So I point kind of at the bottom half of the molecule, and that's my negative area. Okay, that is it for chapter 3.